Okay, people, it is time for us to gather once again to begin. My name is Fredrik Logevall. I know most of you, and I'm just delighted to have this opportunity to introduce this week's fellow speaker. And it's going to be, I think, especially for the humanists and the social scientists in the room, which is basically all of us, I think. It's going to be an interesting session, I think, as Eliel talks to us about his research and his project. I want to introduce him and then turn the floor over to him. Just really good to be with you, and if there's anybody who's tuning in from afar, welcome to you as well. Eliel Camargo Molina is a fellow, of course, at SCAS this year. He was, I think, for the previous 2 years, a Carl Trygger postdoc here at Uppsala. So he's been here in town for a while. He did his undergraduate work at Simón Bolívar University in his native Venezuela, and he actually has a master's degree from Uppsala. So he was here in a previous iteration. His PhD, however, is from Würzburg in Germany, 2015. He has subsequent to that held postdocs at Lund, Imperial College London, and of course, as I noted before, here at Uppsala. He has 25 publications to his credit, and of course building, but 25 at the moment with 950 citations in total, probably 950 plus. I'm guessing today probably there was another citation somewhere. He is a board member of Gambit, which is a collaboration among 70 plus scientists using supercomputers to test new physics theories using massive amounts of experimental data. Just saying that is, I want to read that again, but I won't. So that's Gambit. So he is a key member of that enterprise. He also continues to be, though he's no longer a postdoc at Imperial College, he is still a visiting researcher there. In addition, Eliel has co-founded the Art and Science Initiative, which is a nonprofit facilitating art-science collaborations. That would be interesting to hear about. He is a board member of, or a member of Resilience Frontiers, which is a United Nations-driven multi-year future envisioning process to address the challenges of climate change. Not only that, ladies and gentlemen, in addition, and some of us have heard a little bit about the following, and I wonder if we'll get a question or two about this, but he has a development deal with a Hollywood producer to write a film using artificial intelligence, AI. And this, he and his, I think, collaborator will turn into a podcast, a science communication podcast soon. Eliel, by the way, promised me that I could be his +1 at the Academy Awards when he wins, if his girlfriend can be, if she can get her own ticket as a producer on the film, I can be the +1. So just want to throw that in. He's also a data science consultant, translating the know-how and methods from fundamental research into solutions, both inside and outside academia. Today's presentation by Eliel is The Phase Transitions of Our Universe, when the smallest things transformed the largest thing we know. Eliel, welcome.
Great. Let me turn this on. All right, is the sound working? Yeah, now it's working. Okay, so at the dismay of poor Bjarne, I'm going to walk around here and play with the camera setup a little bit, but I need to move when I talk. Thank you, Fredrik, for such a wonderful, I think it's the best introduction I've ever had. Thank you very much. And yes, so let's get to business, because I want to tell you a story. And I want to tell you a story that shows when one tiny particle, just one, changed the whole universe, the whole properties. It gave rise to the laws of physics that we know today and made life, atoms, matter, everything we know possible. But to do that, well, it's a tall order. So we are going to take a trip through all scales in the universe, and we're going to pick up Lego pieces along the way that then will allow me to tell you without absolutely any dumbing down what all of this is about. And also my research. I'll sneak that along the way. So let's start. Let's get into it. So the first thing I want to talk about is already in the title, phase transitions. What are they? So phase transitions are not just about the universe or particles. It's a physical phenomena that shows up in many places. So phases, when I say phase, it's just a technical word for naming the states of a complex system. A complex system might have several states, and each of those phases, each of those states have different properties, and sometimes they can be completely different. Think, for example, of water. Liquid is a phase, gas is a phase. Still water, but they have very different physical properties. And sometimes those systems change from one phase to another. And turns out that this kind of very general way of talking about this has also a very strong grounding in mathematics and mathematical models that explain all of these different phenomena in different systems in a way that we can use to make predictions. So how that works, and just a little, and we're going to talk about this along the way, but just a little taste of what that means is all of this is connected to the idea of an energy. Depending on the system, you define something that is an energy that has certain properties, and those phases correspond to the minima of that energy. And then by putting it in that language, this is part of all the mathematical framework behind, we can use it to make predictions. So, as I said, water boiling is an example of a phase transition. You put water, you put heat in, and then you have this transition from water to gas. But also, if you take a magnet, a permanent magnet, and you heat it up enough, all the atoms that were aligned producing this magnetic field will just go random. And when you cool it back down, it's not a magnet anymore. So you have this transition from something that was a magnet to something that wasn't a magnet anymore. And that's also a phase transition. But also in elections, for example, and social phenomena. Some people have done work. There's a couple of analyses of, for example, the results of the Trump election, using all of these formalisms to try to understand the rough properties of, whatever representation things have in the system, give you an interpretation of what's happening through this model. That's very technical, but before we go even more technical, I want to do a little game with you. And this game is going to help us develop a little bit of intuition about what we're talking about, and it's going to be helpful. So let's do it. So the setup is that, we have very good separation here, 2 halves of the room. So I'm going to ask half of the room to please raise your hands. This half, this half here. It doesn't matter. Honda, just raise your hands. The other half is going to keep the hands down. I'm going to say go. When I say go, if you're raising your hand, you can choose to either lower it or raise it, keep it where it is, but you have to make a decision, stay the same or change. The goal, and we are all playing together, is that at some point we all have to have the same state, either all with a raised hand or all with the hands down. And let's see how that goes. So I'm going to start saying go. Every time I say go, you take a decision, and let's see how many steps it takes us to get to the point that we're all the same. So go. 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 Look around you. So, we have to work together. Go. 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 We are working together, right? Go. 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 Right, so this seems to be a very complex system that doesn't want to undergo a phase transition. People are not trying to work. But okay, we did an experiment, and this is how experimental science is. Sometimes you get what you expect, sometimes you don't, and then you have to analyze it. So we could jump and do an analysis of what happened here, but we'll do that later. Essentially, if we would have experienced a phase transition, the whole room would have ended up in the same state. And it's just that idea that you have a complex system of things working together, that in some scenarios they actually talk to each other and try to work together, but end up in the same state. But okay, that's the idea. Complex systems, little pieces of it that all work together to create some large-scale change between different states with different properties. Okay, good. Now that we're a little bit more awake as well, let's start going into it. Before we learn about this Higgs particle and how it changed the whole universe, we have to do a little trip. And we are going to do a trip first to the smallest things we know, then to the largest things we know, and then we'll understand how they're connected together. But it all will start here. Here we are in the botanical garden, and because this trip is going to go to many places, we need some kind of anchor. We need something that can keep us aware of where we are. And I've done that by indicating, when you see here in the slides, there's here in the corner this tiny little thing that is just telling you something in meters. What is that? Well, that's the typical size of the typical thing that we are seeing. In a way, some kind of coordinates of where we are in terms of scale. So, botanical garden, typical scale, 10 meters. I'm putting that in math because we're going to have so many zeros that it's necessary. But right now, it's 10 meters, which is 10 to the power of 1 meters. If we zoom in a little bit, we're here. We are at Tumbergsalen. The typical scale of a room like this is a meter. We go even deeper into the human scale. Everything that has to do with who we are, what we experience, what we interact with is typically happening at the scale of around 10 centimeters. But if we go deeper, we still have life there. We have some things like tardigrades that live at much smaller scales, 1,000th of a meter, so 10 to the power of -3, 1 over 1 with 3 zeros. Even deeper, we find cells, tissue. Even deeper, we find DNA, another very exciting field of understanding the laws, fundamental laws of how everything works and how life works, 10 to the -9 meters. And then if we zoom even a bit more, we end up at the place where the unintuitive world of quantum physics starts mattering, where the laws of nature are now, or nature is, as far as we understand, modeled very well by the laws of quantum mechanics. And we can see an atom, 10 to the -10 meters, but we have the typical picture of the atom being this nucleus in the middle and the electron going around. But if we could go in here and look at this, we wouldn't see that. What we would see is a cloud of electrons that we don't really know where they are. We cannot really pinpoint exactly where they are. And this is because of the quantum nature of the issue. And we'll get a little bit deeper into that, but let's go slow. And okay, there's a cloud of things there. But if you manage to go beyond that cloud, what you might see then is the nucleus. And this is something that I think is very fascinating. There's so much space between the electrons outside of an atom and the nucleus in the middle. If an atom would be the size of this room, the nucleus will be the size of a tiny speck of dust. What that means, and let that sink in, is that we're mostly emptiness. We're made out of mostly nothing, right, in terms of space. But what's even crazier is that nucleus is actually made out of other stuff. The nucleus is not like the electron, that as far as we know, we cannot break the electron into smaller pieces. The nucleus is made out of up and down quarks, which in themselves they make what we know maybe more like as protons and neutrons. So a proton is made out of 2 up quarks and 1 down quark. The neutron is made out of 2 down quarks and 1 up quark. But this is also a little bit of a white lie because, again, we are in the quantum world. We don't really know where things are. It's very difficult to count things where they are. Everything is in nature probabilistic, and we understand that the quantum world comes with some rules to it. I'll tell you more about that. So that idea of an electron and an up quark and a down quark making up everything we know, everything we will experience, it is a good enough analogy for maybe school children and maybe first-year students in physics. But then you start understanding that it's a bit more complicated than that. And there's many reasons for that. Why it's not, you can even describe particles as point-like things-ish with quantum mechanics, but we realize very quickly that that's not even enough to describe how nature behaves. And there's several reasons, but I want to tell you about 2 that are very interesting. One reason is the fact that an electron here, an electron in the moon, an electron in Jupiter, an electron in Andromeda, they are the same. And if we're trying to explain this with little point particles, we also have to come up with an explanation. How come there's this thing that appears everywhere and that it looks the same? Same for quarks. So that's a little bit strange. The other thing is that when you go, we cannot really see that because of the lighting, but what we have there is a picture from a particle collider where we throw particles together and make them crash to discover and understand and test all these theories that we have. And in this particular case, it's 2 protons colliding. And they collide, and then a bunch of particles come out. So imagine if you would crash 2 cars and then 25,000 cars come out. That makes no sense, at least not in the macroscopic scale. But in the quantum world and with particles, this is how that works. So how do we make sense of this? And bear with me, this is a very important idea because it's the underlying principle for our best understanding of the building blocks of nature. And they are quantum fields. I'll tell you exactly what they are. But before I go there, let me motivate it a little bit. So quantum fields are this mathematical object that brings together two very important ideas. The idea of quantum mechanics, which I told you a little bit about, which governs the laws of things, the very small things, and that has many consequences, but I'll give you one take-home message of quantum mechanics that is important. Energy is not just a smooth thing, continuous, that comes at every value that you want. It is instead, nature has chosen to bundle energy in tiny little packets. So you only get these little packets of energy. And then you have the idea of special relativity, which is a theory based on or built on the principle, the observed principle that we've seen in nature, that the speed of light is the same everywhere, no matter where you look, no matter where you are, no matter how fast you're moving. You see light moving in vacuum, it's always the same speed. And these two things brought together is what, well, quantum fields, what it did is bringing these two things together. And it turns out that that's the best way to explain the building blocks. So it's not particles, it's fields. Okay, now let's spend some time understanding what fields, quantum fields are. So let's start first with fields, without the quantum part. A field is a very general mathematical object, and it's not that difficult to understand. I'll give you an example. So think about, before we think about an example, I'll tell you what it is. It is an object that for every point in space, through the whole universe, it has a value. And that value, in turn, changes in time. Good. Now, an example. So we have a grounding. Think about the temperature in this room. At every point in this room, we have a temperature. If you're closer to the window, it's going to be colder. If you're around yourself, it's probably going to be warmer. And that's a field, because the temperature also will change in time. So the field will be this mathematical object that I will be able to ask, what's the temperature in this point here? And it would give me a value, and so on and so forth. Another good example is electromagnetic fields. This is a little bit more into the physics. We've gone a little bit further in time, and this is the idea that, you know, there was electricity and magnetism, and people didn't know what it was. And Faraday understood that, well, there's this object called a field that is there, that is the electromagnetic field, and we can use it to do things. We can use it to communicate, we can use it to induce electricity using magnetic fields, and it's this kind of fluid-like thing that is everywhere. And the waves of that fluid is what we call light. So light is actually ripples of that electromagnetic field. It was not only until 150 years later that we understood the incredible importance of the idea of fields. When quantum mechanics was developed, people started looking at the same problem closely. And when you look at light very, very, very close, it stops behaving like waves of a field, and it starts clumping up through the quantum mechanics rules into tiny bundles of energy called photons. It becomes more like a particle. If you've heard maybe the wave-particle duality, it's no duality, it's very clear. At large scales, it's like a wave. At small scales, it starts behaving like a particle. So when you take that idea of fields, and you have excitations of those fields, and those excitations get taken by the quantum laws and bundle up in little ripples, those are particles. So particles are the excitations, the ripples on these fields, quantum fields that are everywhere through space-time. So we have, for every particle we know, we have an associated field, because particles are just a ripple of this field. These fields are all over space, all over the whole universe, and they're just there. But whenever they get ripples, a particle pops up. And you know, I told you that we could make everything we know out of an electron, an up quark, and a down quark. Forgot neutrinos on purpose. Neutrinos are another class of particles that are very light. They're coming from space, from below and up from the top, going through us all the time. I don't have time to go into it. We can talk about it with a coffee. But we have all these fields affecting each other, swimming, going around, clashing with each other. If a field associated with an electron, the electron field moves, it might affect the field associated with the quarks and so on. And at least for the atoms that we can find here in the room, this is probably enough. However, nature was not so kind to us. For some reason that we yet don't understand. We know it is that way, we can describe it, we can make predictions, and we have mathematical models, but we don't have a reason. Nature decided to make 3 copies of the same thing. And the 3 copies are identical with one difference. Each copy is heavier than the one before. Here I've shown, indicated with a number, technology. There you go. With a number here, how much heavier than an electron it is. So the electron is 1, the muon is 200 times heavier than the electron, the tau is 3,000 times heavier than the electron, but they all have the same properties. They're more or less the same, and so on and so forth. On top of that, these particles interact with each other through forces. There's 4 forces as far as we know. 2 of them are very familiar to us, the electromagnetic, but we just talked about a little bit, and gravity, which is why we're here. But then there's also the strong and weak force associated with the fact that quarks clump. The strong force makes the quarks clump together into protons and neutrons, and the weak force is, for example, responsible for radioactive decay. This is what we call the standard model of particle physics, our best understanding of the building blocks of the universe. And the pieces are not particles, are quantum fields. Great. Oh yeah. The attentive listener to this talk might have noticed that I started saying that there's one particle that changed the whole universe called the Higgs, and I haven't even mentioned it. Well, the Higgs is a very special particle. It's a special type of quantum field that has, among other properties, a very, very special property. If you take a box, you take all of these ripples from the fields, all the particles out of this box, you're not left with something empty. Some of the rules of quantum mechanics say, called the uncertainty principle, that roughly nothing can really stand still. You have fluctuations. You have things that ripple, and the vacuum then is not really empty. But besides those fluctuations, it mostly is, right? And all of these fields, electrons, quarks, that when they bundle up produce particles, if there's no particles there, they're kind of quiet, typically mostly 0 on average. They don't do anything. The Higgs is so special because, in particular, it can get away with being not 0 when there's no Higgs particles in it. It can actually have a constant value. And I'll tell you what that means in terms of physical implications. But in our modeling, in our understanding, theoretical understanding of our description of how nature behaves, that has a profound consequence. Making the Higgs have a non-zero value everywhere costs energy. To have a field have any value costs energy to the universe. But the universe is lazy. One of the most fundamental principles in physics is that the universe wants to minimize energy, the principle of least action. The universe says, what am I going to have to put more effort, this or this? I'm not going to do that. I'll do the easy thing. And that energy, how much it costs, depends on when in the history of the universe you ask that question. So for the Higgs today, that energy looks like this. Bear with me for a second. I know it's a lot of things happening in this plot, but hopefully I'll take you through it. So on the y-axis, we have how much energy it costs. Here on top, it costs more energy, down less energy. So all of this part on top is very expensive. This is not so expensive. This is the actual energy. So we have to be somewhere in this curve. This is the amount of energy that it would cost you to give a Higgs a certain value, which the value is here on the x-axis. So here in the middle, we have 0. That's the Higgs field having a 0 value everywhere. And that, as you see here, it's expensive. It costs a lot of energy. But there's this place here where you have a non-zero value, let's call it V, and that actually is much cheaper. It's much less energy to be here. So that's actually the value that the Higgs has everywhere now today. And it's non-zero. What does that mean? Well, what that means is that you have all these fields, one field for each particle, clumped up together by the rules of quantum mechanics, so on and so forth, going around on this sea of Higgs. Not particle, field, that is non-zero. And they're swimming through this, and this is bringing some resistance, and it's changing the ways that all of these things interact with each other. And that kind of interaction of this Higgs field with all of the particles is what we call mass. Is what makes an electron have a mass, what makes a proton and a neutron have a mass, mostly, and what makes matter have a mass. The fact that you weigh 50 kilos, 40 kilos, that is because the Higgs has a non-zero value. That's the origin of that. So if the Higgs would be 0, nothing would have mass, atoms wouldn't form, we wouldn't have matter, we would just have a bunch of particles going at the speed of light with a lot of energy everywhere. So in this case, I have here a little illustration. Imagine this is like an electron and a quark or whatever your favorite particle is. And they're in this sea of Higgs field. and they interact with each other through some mediator that could be one of these forces. That, by the way, there's also quantum fields associated with the forces, but I didn't go there. But you think that everything is written in terms of quantum fields, and they interact, but this kind of resistance is what's bringing the mass. So what happens if we go even deeper, to 10 to the minus 35 meters? This is what we call the Planck scale. This is the point where I tell you, very gladly and very happily, we don't know. This is a point where, in my opinion, this is the scale at which the most important question in theoretical physics lives. Because at those scales, that uncertainty of quantum mechanics, that law that says that quantum mechanics doesn't let anything sit still, that allows for the freedom in our models to have such large uncertainty that we have enough energy to produce black holes spontaneously from the vacuum. Crazy. And that's not what's happening. So then there must be something wrong about our theory. And that's another way of putting that question, that we don't know how to reconcile the theory of gravity with quantum mechanics. I'll touch a little bit onto that, on my work and ideas and my time here, and I'll tell you a bit later. But let's go back. Let's go back to here, to the botanical garden. And let's start zooming out. I like zooming out. I like zooming in, because then we go to particles, my favorite thing. But now we're zooming out. I like it because now I can show you real pictures. This is a real picture. This is taken by a satellite of Earth and the moon in front of it. And the scale is 10 to the 6 meters, around the radius of the Earth. We zoom a little bit out. We have the solar system. Here we have Venus and Earth. If you have very good vision, you can see these tiny white dots there. That's Venus and Earth, and that's the sun in scale, taken by the Voyager 1 spacecraft. Zoom out, we have galaxies. This is Andromeda, the closest galaxy to us. We zoom even more, and we have many galaxies that clump together. This is a picture from the James Webb Telescope, recently launched. I would love to have another hour to talk about this, but I don't. But then galaxies clump together at larger scales. And if we go even at larger scales, we are at the observable universe, where we have these large-scale structures that a lot of people mention that they look a lot like a brain. I think it's fun that it does. So the observable universe, what is it? You know, you probably all heard that the universe is infinite. And that's true. But the universe is not infinitely old. It has an age. And as I told you, light has a speed. It cannot go infinitely fast either. So there are things in the universe that are so far away from us that in the time the universe has been alive, there hasn't been enough time for that light to reach us. So we cannot see it. That's the observable universe. And the more attentive, or let's say the people that drank more coffee after lunch might have noticed the fact that what the observable universe is grows with time. Because the more time that passes, the more light from things can reach us, and then it starts expanding. But anyway, today, there's something we call the observable universe. It's 10 to the 26 meters, more or less, and very cold, minus 270 degrees centigrade. What is it made of? So through means and experiments that are super interesting on their own, the cosmic microwave background and so on, if you want to research about that, but we figure out a way to understanding what the universe is made of. And it's made of 68% dark energy, 27% dark matter, 5% ordinary matter, which is what we are made of. And dark energy and dark matter, they have those names because we don't really know what they are made out of. We know what effect they have in the physical laws. Dark energy is responsible for the universe expanding. Dark matter is responsible for keeping galaxies together with gravitational force, but we don't know what they're really made out of. But we know what we are made out of, ordinary matter. That matter is mostly matter, and a tiny sliver of antimatter. But the standard model of particle physics, this model, the best model that we have, says that there should be more or less the same amount. So this is one of the biggest questions, including also dark matter, dark energy, that the standard model leaves open, even though it's the most successful theory with the most precision to experiment, unprecedented in any other area of science, where we have predictions for things about the particle world to the 11th decimal place, and it's insane. And at the same time, there's this dichotomy. There's such big questions about the universe that remain still open, and the standard model is not enough. So finally, we're getting enough Lego pieces to start building a little castle of the story of when the Higgs changed the whole universe. But we need to do one more thing. We need to understand what happened back in time. As I told you, and I showed you that plot of the Higgs energy today, it's not always been like that. It's not always been the most lazy for the universe to be in this point where the Higgs has a non-zero energy. If we go very, very early to 10 to the minus 30 seconds after the Big Bang, after a period of quick expansion called inflation, the universe was pretty hot. It was not so cold as it is today. And the potential energy of the Higgs looks like this. What that means is that, there's nothing here. The energy only allows me to go to this place here. That's the cheapest place, and it's when the Higgs is 0. So at this point, nothing has mass. There's no atoms. There's nothing. Everything is super energetic and flying around really fast. When the universe starts cooling down, that potential starts changing. And then you have this candidate place that looks like a cozy place where I could go. But it's still more expensive in terms of energy. So we'll stay here in the middle. We're still here in the middle. And if the temperature goes down, this new place, now it's even more cozy because it costs the same energy to be here. You see, it's the same than here, but the Higgs is non-zero. So this starts looking like the place we want to be if we want to have matter and life and everything we know. But we're still here, and it's really difficult to go there. There's no reason why going there. We're not going to gain anything. And then when the universe cools down, two things can happen. Option A, the potential starts looking like this. We were here in the middle. And then there's this new place here to the right where we could roll down to that costs less energy, and the universe might say, okay, let's go there. And it would do so slowly. So it would start rolling. The Higgs would start from 0, having a non-zero value, and slowly going from 0 to some other value, and things getting mass, and maybe atoms form, and so on. That's what the standard model predicts happened. There's another option. And we have very good reason to believe that this might be what actually happened. And both reasons based on hints in experimental results, but also theoretical physics reasons of this would fit very well in helping answering a lot of those open questions that I told you about, and I'll tell you how. So let's focus on this second option. And when that potential function looked like that, the universe was much younger than today. We're talking about 10 to the minus 12 seconds after the Big Bang. What we call today the observable universe was way smaller, was around the size of a big star, and the universe was much hotter, like 10 to the 15 degrees centigrade. So we are here in this hot universe. The Higgs function looks like what I just showed you, with a thing like that. And the interesting thing is, okay, what happens then? We are here. There's a very nice place here. But there's a wall in the middle. If you see, if I want to go all the way there, I have to jump through this, and that costs energy, and the universe is like, no, I don't want to do that. But we are living in the world of quantum physics. The Higgs field is a quantum field. And quantum physics brings with it a lot of unintuitive phenomena. One of them is called quantum tunneling. This is essentially what's powering transistors, why transistors work the way that they do. And that's why your phone works. So it's a natural phenomenon. It's not weird. There's nothing weird with quantum mechanics. It's just at a scale that we are not familiar with in our human experience. But this is the way nature works. So what can happen also, because part of the laws that the Higgs field borrows from the quantum world is the fact that there's this uncertainty and there's this jumping around and fluctuations and so on, which can mean that we're here and we can just tunnel through here suddenly. So a little bit a way to see it is the fact that if you're not really uncertain where you are, there might be some probability that you actually aren't here in the same place, but you were here. When I say here, in terms of the Higgs field value, this is not space. Remember that this Higgs field is all over the universe, right? So it's a little bit of an abstraction in the sense that there's a wall here, not in space, but in this potential function. But the idea is that quantum mechanics allows you to just cross. Great. So we are there. That happens. How does that look like? So this is an interpretation of how that might have looked like. So when that happens, that sudden transition happens, what happens is exactly the same as with boiling water. Water is boiling. You have bubbles of steam that pop up, that they grow up, and they start expanding with steam inside and replacing all the water in it. The same would have happened with the universe. You have a bubble inside which the Higgs field is non-zero. You cross that border. That bubble starts expanding. Other bubbles start appearing everywhere. They start expanding. Outside of here, nothing has mass. The Higgs is 0 everywhere. Inside the bubble, things have mass. and we have all of the ingredients necessary to build the world as we know it. Moreover, and this is very interesting, and this is why we're interested, one of the reasons why we're interested, what would happen also if the right conditions are met in the model and the bubble wall, and this depends on what theory you're thinking about, and remember that the standard model says this didn't happen, but the standard model has many open questions. So depending on what extension of the standard model, what other theory you might think, the properties of these bubbles might be different. And if you find the appropriate description, and we found many such descriptions, what could happen is that matter is actually able to go through these walls, whether antimatter just bounces off. So as these bubbles expand, antimatter starts bouncing off, a little bit of antimatter gets through, but matter just crosses, and we end up, it goes from being here super light, no mass, to going inside having mass, giving us all the ingredients to have atoms and everything we know. And finally, all these bubbles expand, and we are in the universe today, and we have an explanation for why there's so much little antimatter than matter. Right. So it's a good story, right? Well, at least I think it is a good story. But can we find out what really happened? And this is the thing. Theoretical physics is all about figuring out whether our ideas are describing nature correctly. It's not about not caring whether something is real or not. And also the question about whether it's real is a very deep question. I'm talking about, a successful description of phenomena that we see through the scientific method. And we want to do that. So can we find out what really happened? The answer is yes. And it's very exciting how we can do this. But before that, the last Lego piece, general relativity, the law of gravity. How does gravity work? This is the last missing piece that we need to understand. How the heck are we going to be able to measure this stuff? So some of you might have heard the way that this works. You have space-time. Space-time is, and I should have described it earlier maybe, but you know the idea of space. It's some place in three-dimensional space, and time, something that flows. We physicists put them together into a thing called space-time. So when you think about a field that has a value at every point in space and it changes in time, we just say it has a value in space-time because it has a coordinate not only in space but also in time. Space-time is this fabric upon which everything is built on top of. And actually, it turns out that space-time is the field, not a quantum field, a normal field, associated with gravity. So gravity is also explained with a field, and that field is the fabric of space-time itself. Okay, if you're a little bit dizzy, it's okay. I was dizzy the first time I heard that, but it's super interesting. And it turns out that you can visualize it simply if you think that space-time is just, instead of 3 dimensions, it has 2, like a fabric. And then you put something that has a lot of mass. That mass is going to distort it. It's going to bend it. And that bending of space-time is going to affect everything that lives there. So in particular, if you see this, just the way that it looks, a heavy ball on a piece of fabric, and you think that you take a little green ball, and you throw it, it's going to start going around because of the curvature, because it's pulled down like that. And this is exactly, at least in a two-dimensional world, if I would try to write down the laws of gravitation of planets orbiting the sun. And this, you could think of it as Earth going around, and the sun is bending space-time so much that that's what happens. If you put something here, it would fall down in the same way that if you throw something towards the sun, it's just going to go into it. General relativity is that. Bear with me. This is the last Lego piece, I promise. And they are described specifically with a set of equations called the Einstein's equations, because theoretical physics is not just about saying this is related with this. It's about a very specific framework that connects those things in a very specific way that allows us to make predictions about nature. So we have Einstein's equations, and what they have is a lot of mathematical objects, but the important thing is that on the left you have some object that encodes the wiggleness of space-time, another one that encodes this cosmological constant, which is something that is shoehorned in a way to explain what the universe expands. We don't really have a first principles derivation of where this comes from, but we know that if we put it there, the universe expands. What space-time is made of, and then finally, that whole thing, that is the shape of space-time, is related to this stress-energy tensor that has in it all the information about the mass and the energy that are there. So the more mass, the more wiggleness and curvature. And there you go, that's general relativity for you. So what that means is that when we have these bubbles expanding, these bubbles expand, they collide. I told you that things outside the bubbles have no mass. inside the bubble, they have mass suddenly, and so you have this mass energy incredibleness, like universe-wide phenomenon going around. What that means is that that thing is going to make space-time ripple. That thing, because it's a lot of mass and energy coming suddenly, clutching and everything. Imagine if I would take that example of the sheet and put a bunch of heavy balls crashing with each other. Then the whole thing was going to wiggle. And space-time wiggles. And those are what we call gravitational waves. And we just recently managed to experimentally verify their existence by measuring the ones that come out of two black holes merging and clashing with each other, a pretty big phenomenon as well in terms of mass and energy. But also this phase transition that might have an explanation for why there's so little antimatter, might have left an imprint of wiggles in space-time. Not only that, and I want to let this sink in, we're going to be able to measure this. And we're going to be able to measure this. We've seen some gravitational waves on Earth. We're going to send a satellite called LISA, which is 3 satellites that shoot lasers at each other and whatever. And super, super fascinating stuff that is going to be able to see these wiggles in space-time. The plot lost a piece there, I don't know why, but I can just draw it for you. There's a thing here in the plot, which is this LISA sensitivity here. The thing what we have here is on the x-axis we have the frequency, how fast those wiggles wiggle, and on the y is like how strong they are. And here in the white line you have how those wiggles of space-time would look like for a phase transition like the ones we're talking about with these bubbles and so on. And on top, in this green line that I drew, is what this satellite is going to be able to see and measure. And you see there's an overlap. So for a large family of phase transitions like this experiment is going to be able to see whether we actually, as opposed to what the standard model says, we had one of those strong transitions with bubbles. And this is fascinating. I mean, let that sink in. We're talking about measuring with a satellite something that happened not that long after the Big Bang, and getting answers about how that relates to the very fact that there's matter and that we are here. So, finally, last Lego piece. Now I'm gonna give you 2 examples of new ideas that I'm exploring while I'm here as CAS. It's not an exhaustive list, but it's 2 examples that I wanted to tell you about. So there were many phase transitions. And this is a very heavy plot, but I wanted to show you the real plot. This is the plot that I put when I do grant applications. And I didn't want to dumb it down. But at the same time, I think it's a very good device to explain something to you, a very deep thing. Here we have the whole history of the universe. The Big Bang, universe appears. Then we have this period of rapid expansion called inflation, which is something that we need to be able to explain how the universe looks today, given that it came out of the Big Bang. So the universe needed to expand very rapidly in the beginning to have the properties that we see today. So just believe me. I can tell you more about it with coffee. But since then, up until today, there were many steps along the way where phase transitions happened. We know that they happened, but we don't know how many. And we don't know the exact characteristics of them. And the reason we know that they happen is because here we are. There's matter, there's mass, there's all of these things. There's another phase transition related to the fact that quarks clump together into protons and neutrons. This is also something we see, and it's also connected to maybe a phase transition that one at least that happened along this way. And now we're opening this window to understand all of these things. So we know there were several. We know, as I said, know their characteristic, and knowing more about them holds the key to big open questions about nature. And these mind-blowing experiments are along the way. So can the theory be ready? So in general, let's say this satellite comes out and it measures these wiggles. And we know those wiggles mean there was a transition. But to what exact extension of the standard model does it correspond? And that in general is a very hard answer. We're just about developing the theoretical methods to answer that question. But there's another question that I am starting to work on, which is, okay, in general it's difficult, but are there some theories that go beyond the standard model that if they trigger one of these transitions that would explain the matter-antimatter asymmetry, would they also be easy to spot when that satellite goes out and sees the data? And one of those examples is when, for example, you have such a phase transition happening where you go from one part of that potential energy of the Higgs field to another through the quantum tunneling, and then when all the physics and laws change after that transition, in the same way that we end up without mass, end up with mass, start without mass, end up with mass, the whole laws of physics change. They might also change in a way that changes the shape of that potential, and it might invert the hierarchy of these minima. So we start from here, we say, oh, there's this cool place to go with less energy. Jump there, the properties of, the laws of physics change, that thing inverts, and now we can go back, and we go into a cycle of these phase transitions, no? And that would have a very particular signature. And this is something that we would see right away. It's not only, oh, there was a transition. Which theory does it correspond? We don't know. If we see something like this with peaks, for example, then we know. And there's a lot of ideas like that of what theories do we spot right away when these satellites go around. Another idea is the fact that during this period of rapid expansion called inflation, the universe was also very curved. The universe was so curved that gravity starts playing a role. So then we go deep into that problem of how do we reconcile the quantum world with gravity. And that means that the laws are slightly different, and the way that these transitions work is a little bit different. And the theory side here is totally interesting, still under development. And many phase transitions could have happened along this time, including some that would have destroyed all the laws of physics that we have today. But we know those didn't happen because we are here. And the question is, what does the standard model predict about this? If the standard model predicts something that couldn't have happened, that is even more reason to believe that we need to go beyond the standard model. And to calculate this, it's really hard. You have to bring together gravity and quantum field theory, and people don't fully understand how to do that. And I've worked on using stochastic methods where the quantum part of this problem gets modeled through some random noise in a way that it conserves enough properties to make the calculations still meaningful, still creating predictions about what would have happened in nature, but also much, much easier. And this is part of the things I'm trying to develop, try to understand, answer all those questions. Are we capturing what we want? Is this agreeing with the state of the calculations where people just do full-on quantum field theory with the quantum stuff and so on? And this is what I'm going to be thinking about. Finally, how much time do I have left?
You have, sir, about
5 minutes. That's beautiful. So I wanted to send this message. SCAS, it's an institute for advanced study. And it has a long tradition, as we all know. And part of that means that one of the reasons I'm the most excited for this time here is not only about going through those ideas that I've already had and exploring them, which I will do, of course, but also having the time to slowly reflect and understand the breadth of the area that I'm working in. So to illustrate that, Matthias showed me this book, which is amazing. I think SCAS bought like 30 copies or something, so I suggest each one of you go take one and read it. But this is an essay written by Abraham Flexner that started the Institute of Advanced Studies in Princeton. And he says there was this young mathematician that was, after a year, SCAS came to say goodbye. And he says, mathematics is developing so fast. I kind of like, I need to keep up. And after this year, the blinds are raised. I was blind, now I can see. And I have already 2 ideas for papers that I shall shortly write. So the output is not measured in terms of like, okay, well, he didn't write there, oh yeah, I wrote 400 papers when I was here. It was more about, I had the time to delve deep into ideas. And then, how long will this last? 5 years, perhaps 10. Then what? I shall come back. There's this rule in Institutes of Advanced Studies that after 5 years you can, so it's based on this deep concept. And this was written in 1938. Back then, a mathematician was already like, I don't have time. So just to reflect on the value and my excitement that I don't necessarily know where I'm going to get to, but I'm so excited about the journey. And finally, an epilogue. And this is touching a little bit on all the artificial intelligence things that I do as a hobby that is becoming more of an important thing. I think we are at the age of artificial intelligence. As a parallel, most of what I just told you about physics, fundamental physics, which started way closer to philosophy than to probably even mathematics, and developed into something heavily relying on complicated calculations. All of those ideas are only possible because we use computers to calculate these things. Computers came, revolutionized mathematics, computational, everything nobody multiplies numbers in their head anymore. Statistics, big data, all of that stuff. So just in the same way that computers transformed my area, the natural sciences, computers are about to transform humanities and the social sciences. Because we have artificial intelligence that in the same way that computers could very naturally calculate this, do these super complicated calculations for us that we knew how to do, but it did it faster and in a different way, it became a tool. Computers are now being able to offload from us cognitive tasks, helping with translation, searching text, using ideas and concepts. It's a new kind of collaborator. It's bringing the idea of computers now being able to be a new kind of collaborator. And it's a good thing if we make it be a good thing. If we start embracing this, understanding it, and incorporating it into our practices. But for that, we need a little bit of translation, a little bit of bridging. And I'm here at SCAS, and I think I can help a little bit with that bridging. And I'm super excited about everything that you all think about and ready to talk about how we can jump into this as well. So this is also part of fulfilling the task of telling you what I'll be doing when I'm here at SCAS. And with that, I finish. Thank you very much.